Lecture 29, Memory Enhancement and Hippocampus Prosthetics. Let us begin not in the present moment, but in its absence. Picture a man standing in his kitchen, holding a steaming cup of coffee, and realizing, again, that he has no idea how he got there. The coffee is familiar. The room is his. But the continuity is gone. Each day, each moment, exists in isolation. He can recall his childhood, his wife's name, a war he fought in the 1960s, yet nothing of the last 5 minutes. His hippocampus is damaged. Without it, memory is no longer a flowing narrative, it is a series of isolated islands, each cut off from the next by an unbridgeable gulf. This is not a thought experiment but the lived reality of people with profound anterograde amnesia, those who cannot form new memories despite otherwise normal intellect. The most famous was Henry Molaison, known as HM, who in 1953 underwent an experimental surgery to cure his epilepsy. The surgeon removed HM's medial temporal lobes, including the hippocampi, and indeed the seizures stopped. But so too did the ability to turn the present into the past. For the next 50 years, HM lived in a 10-minute window, constantly waking from a dream, as he described it, with no storage of new experiences. He could learn motor skills and habits, his implicit memory remained intact, but he could not remember people he met or events that just occurred. The surgery taught neuroscience a crucial lesson. The hippocampus is the linchpin of forming new declarative memories, facts and events, even though other types of memory, skills, habits, rely on different brain systems. In essence, HM helped reveal that memory is not one thing, but many, and that the hippocampus is essential for weaving our day-to-day experiences into an ongoing story. That missing story is precisely what memory prosthetics seek to restore. Not metaphorically or vaguely, but in a direct, technical sense, to interface with the hippocampal memory system, record the encoding of an experience, and write it back when the brain's own machinery fails. In short, to implant a bridge across time. It sounds like science fiction, building an artificial device to repair or even enhance memory, but over the past 2 decades it has inched into reality. In this lecture, we explore that radical possibility of hippocampal neuroprosthetics, a technology that aims not just to assist memory but to become part of the memory process. This is where brain-computer interfaces move beyond read-only, merely sensing brain activity, and become write-enabled, actively modifying the brain's patterns. It is an intersection of neuroscience and narratology, for what is memory if not the brain writing its own narrative? To grasp how one might artificially restore memory, we must first ask, how does the brain create memories in the first place, and how did we come to know what we know about this? The journey toward memory prosthetics didn't start with computers or electrodes, it started with puzzling observations, bold theories, and decades of research into the nature of memory itself. The search for the memory trace. Long before anyone imagined electronic memory implants, scientists struggled to answer a fundamental question: where and how are memories stored in the brain? In the early 20th century, a prominent psychologist named Carl Lashley embarked on a quest to find the physical trace of memory, the engram. Lashley trained rats to run mazes, then systematically removed or lesioned different parts of their cortex to see if he could erase the memory of the maze. To his surprise, no matter which area he removed, the rats still retained partial memory of how to navigate. What seemed to matter was not the location of the lesion, but the amount of tissue removed. The more he cut, the worse the rats did, but there was no single spot that, when cut, wiped out the memory completely. In 1950, after years of such experiments, Lashley conceded defeat. He proposed 2 principles: mass action, the idea that memory is distributed across the brain such that the cortex works as a whole in many tasks, and equipotentiality, the idea that if one part of the brain is damaged, other parts can take over its function. In Lashley's words, memory appeared to be not localized to a single area but spread throughout the cortex. His famous conclusion was that the specific engram had eluded him, leading him to suspect that memory might be so distributed that it cannot be pinpointed in a single neural substrate. Lashley's results were perplexing. They suggested that complex memories, like a learned maze, weren't neatly filed in one region, but rather woven across the brain's networks. Around the same time, other researchers were approaching memory from different angles. One of them was Wilder Penfield, a neurosurgeon in Montreal, who treated severe epilepsy by surgically removing focal brain regions. In the 1930s and 40s, Penfield pioneered surgeries on awake patients under local anesthesia. As he stimulated different parts of the brain with a gentle electrical probe to map their function, so he could avoid critical areas during resection, he stumbled upon something astonishing. Occasionally, a patient would suddenly recall an old memory or vividly relive a past experience when a particular spot in the temporal lobe was stimulated. A mild current to the cortex, and the patient might report, "I'm hearing a song from my childhood," or "I see my schoolyard, just as it was." One famous patient, when Penfield's electrode touched her temporal cortex, found herself back in a memory of a young girl in a field, hearing a familiar voice, a forgotten scene that played out in detail until the stimulation stopped. These flashbacks were sporadic and not under precise control, but they hinted that specific memory traces could be reactivated by stimulating the brain. It was as if the stored experiences were lying latent in the tissue, and the electrode's current opened a door to them. Penfield's experiments were among the first proofs that specific memories have physical footholds in the brain, even if distributed. And interestingly, the region that most often evoked such memories was the medial temporal lobe, the very area that, a decade later, would be removed in patient HM and produce such profound amnesia. By mid-century, then, two seemingly contradictory views of memory emerged. Lashley's work suggested memory was everywhere and nowhere, smeared across the cortex. Penfield's findings implied that distinct memories could be triggered from specific regions. The resolution to this puzzle began to emerge in the 1950s and 60s through cases like HM and the work of neuroscientists such as Brenda Milner. HM's case demonstrated that the medial temporal lobes, including the hippocampus, were critical for forming new declarative memories, even if older memories or habits survived the loss. Psychologists also distinguished between memory types, short-term vs long-term, declarative vs procedural, etc., and realized these might have different neural substrates. Psychologist Donald Hebb proposed in 1949 a theory that would become foundational, that memories are stored through the strengthening of connections between neurons that fire together. This idea, often summarized as cells that fire together, wire together, suggested that the brain encodes information by changing the synaptic strengths in cell assemblies. Hebb's theory put forth a mechanism, synaptic plasticity, that could reconcile distributed storage with specific engrams. A given memory might correspond to a network of neurons firing in concert, rather than a single cell or spot in the brain. The search then shifted to identifying these networks and the processes that strengthen synapses. A breakthrough came in 1973, when scientists Tim Bliss and Taya Lmo, working with rabbits, discovered long-term potentiation, LTP, in the hippocampus. They found that by giving a burst of high-frequency stimulation to the input pathway of the hippocampus, the perforant path into the dentate gyrus, they could produce a long-lasting increase in synaptic strength, essentially, a persistent memory trace at the cellular level. This was the first direct demonstration of Hebbian plasticity in the brain. It showed that the hippocampus wasn't just a passive relay for memory, it was a workshop, where the connections between neurons could be durably modified. And tellingly, it was observed in the very trisynaptic circuit of the hippocampus that had been anatomically mapped by Ramon Y. Cajal and others, entorhinal cortex dentate gyrus CA3-CA1. This loop, sometimes called the trisynaptic loop, soon became seen as the core of how the hippocampus encodes new experiences. Each component of the circuit seemed to contribute a different operation to memory processing. Over the ensuing decades, research filled in many details of this hippocampal memory system. In 1971, John O'Keefe discovered place cells in the rat hippocampus, neurons that fire when the animal is in a specific location, effectively forming an internal map of space. O'Keefe and Lynn Nadell later argued that the hippocampus constructs a cognitive map of the environment, tying together the elements of an experience by their spatial context. Others found that hippocampal neurons also code for time, so-called time cells, and for specific combinations of cues, suggesting the hippocampus encodes the context of events in both space and time. Computational theorists like David Marr and James Anderson proposed early models of hippocampal function. Marr, in 1971, postulated that the hippocampus functions as an auto-associative memory, capable of rapidly forming links from sparse inputs and later completing the memory from partial cues. In the 1980s, Bruce McNaughton, David Barnes, and others elaborated the idea that CA3, with its dense recurrent connections, could act like a content-addressable memory, a Hopfield network, where a fragment of a pattern would attract the full stored pattern via pattern completion. Experimental evidence later supported this. CA3's recurrent synapses exhibit Hebbian plasticity and can indeed retrieve complete memories from partial input, behaving as an attractor network. Meanwhile, the dentate gyrus was hypothesized to perform pattern separation, orthogonalizing inputs so that similar experiences, say, two visits to a cafe that look alike, get stored as distinct neural representations and won't overwrite each other. CA1 was thought to be a comparator or translator, aligning the processed hippocampal output with neocortical inputs. By the 1990s, a picture had emerged of the hippocampus as an indexing system. It rapidly encodes new experiences by linking disparate elements, who, what, where, when, into a coherent memory trace, which can later be completed from any unique part of the pattern. These traces are initially fragile and hippocampus dependent, but over time, through a process called systems consolidation, they are thought to be fed back to the cortex for long-term storage, leaving the hippocampus free to index new memories. This complementary learning view explained Lashley's earlier findings in a new light. The reason he couldn't find a single engram in cortex was that complex memories aren't in one spot, they're distributed across networks that the hippocampus helps bind. Remove enough of the network and the memory degrades, mass action, but small removals can be compensated by the remaining network, equipotentiality. In sum, by the turn of the 21st century, scientists understood the hippocampus not as a camera that records experiences, but as a conductor and librarian. It conducts the encoding of an experience by coordinating neural ensembles, and it serves as an index that can retrieve those ensembles later. It operates in concert with the rest of the brain, notably the prefrontal cortex, which plays a key role in organizing memories, selecting what to remember or forget, and using memories to guide decisions. In fact, during memory retrieval tasks, the prefrontal cortex and hippocampus engage in a tight dialogue, often synchronizing in theta rhythms. The prefrontal cortex can be seen as the manager that queries the hippocampal index when you need to recall something. Each part of the hippocampal circuit has a unique contribution. The dentate gyrus separates patterns. Imagine encoding two similar rooms with different decor. The DG helps ensure those memories don't blur together. CA3 links the bits into an associative net, so that just smelling the coffee in that room might later trigger the memory of the entire scene via pattern completion, and CA1 outputs a refined code back to cortex, like a final draft that can be understood and stored elsewhere. Importantly, all this happens in the language of neural activity rhythms. The hippocampus generates distinctive oscillations, especially the 3 to 8 Hz theta rhythm and sharp wave ripples, that time coordinate the dance of neurons during encoding and retrieval. Theta oscillations, for example, often reflect a sort of alternating current of memory. Roughly speaking, the troughs of theta, in rodent experiments, correspond to moments when new information is written in encoding mode, and the peaks correspond to moments of recall or internal replay, retrieval mode. The brain, it turns out, separates the act of writing a memory from the act of reading it, cycling between the two states several times per second, perhaps to avoid interference. All these insights about circuit function, rhythms, plasticity set the stage for a bold question. If the hippocampus is a machine that performs identifiable transformations on neural signals to form memories, could we replicate those transformations artificially? If memory is not a mystical property of the soul but a set of neural codes and operations, perhaps those could be modeled, and when the biological system falters, a device could enforce the code and rescue the function. This is the vision that researchers like Theodore Ted Berger at USC began championing in the early 2000s. Berger, trained in both neuroscience and engineering, proposed that it might be possible to create a hippocampal prosthesis, a device that could take in the electrical activity of neurons in the hippocampus, run it through an electronic model mimicking what the hippocampal circuit does, and output signals that could drive downstream neurons, thus replacing the memory encoding function of a damaged hippocampus. It was a radical idea, bordering on heresy. It implies that memory can be abstracted as an algorithm, a set of input-output relationships that, at some level, can be captured in mathematics. It suggests that losing one's memory need not be permanent, that if you can patch the broken circuit with silicon, the mind can remember again. To pursue this, Berger and colleagues, including Dong Song and, in collaborative trials, neuroscientists like Itzhak Fried and Robert Hampson, had to break the problem down. First, they focused on the hippocampus's well-defined subcircuit, the communication between CA3 and CA1. In a healthy hippocampus, when an experience is being encoded, a pattern of neural firing in CA3, representing the converged input from cortex via entorhinal and dentate, is transformed into a corresponding pattern in CA1, which then outputs to cortex. By implanting multi-electrode arrays in CA3 and CA1 of an animal, one can record these paired patterns. Multi-input multi-output, MIMO, modeling can then be used to characterize the transformation, essentially, learn a function that maps the CA3 activity to the CA1 activity. Early on, they used a form of Volterra kernel models, a kind of higher-order convolution, to capture nonlinear, time-dependent aspects of the transformation. Over time, this evolved to more sophisticated algorithms, even exploring artificial neural networks, to improve predictive power. In parallel, the team developed high-density electrode implants that can both record and stimulate within the hippocampus. These implants might have, say, 16 or 32 microelectrodes in CA3 and a similar number in CA1, allowing them to sample a population of neurons rather than just one or two cells. The goal was not to record every neuron, that's impossible with current tech, but to get a representative sample of activity and treat it like a vector that could be mathematically transformed. Imagine you're training a device in a rat. The rat is learning a simple memory task, perhaps it sees a light. Then after a short delay it has to choose one of two levers, one will give a reward. This is a delayed match to sample or working memory task. As the rat learns, you record from CA3 and CA1 on each trial. When the rat correctly remembers and chooses the right lever, you log the patterns. This is what CA3 did, and this is what CA1 responded. After many trials, you have a mapping of inputs to outputs. Now, you introduce a challenge, maybe you inject a drug or make a small lesion that disrupts the CA3-CA1 communication, simulating memory impairment. The next time the rat does the task, whenever CA3 activates, with the code for, I saw the left light, your device recognizes that pattern and, instead of letting it die in a now silent CA1, due to the lesion, it stimulates CA1 with the pattern it should be, essentially playing the role of the damaged circuit. The hope is that the rest of the brain, receiving the CA1 signal, will never know the difference. It will be as if the hippocampus performed its job. And if all works, the rat remembers and chooses correctly, despite the impairment. This record, model, and replace strategy has seen remarkable, if initial, success. In rodents, Berger's team did indeed show that a MIMO model prosthesis could restore and even enhance memory in tasks like the one described. In one early study, they reported that when the prosthesis was turned on, rats' performance in a memory task improved significantly compared to when it was off. Notably, they even showed memory enhancement. Normal rats, with the prosthesis augmenting their CA1 signals, performed better than their baseline, as if the device was boosting the natural memory function. In monkeys, similar approaches have improved performance in visual working memory games and decision-making tasks that involve remembering an image or rule over a short delay. By the late 2010s, the research had progressed to human trials. Participants were patients with epilepsy who already had electrode arrays implanted in their hippocampus for seizure monitoring, a fortunate opportunity to test the prosthetic approach ethically, since the electrodes were there for clinical reasons. These volunteers played memory games on a computer, like remembering a pattern or an image for a short while. The prosthetic system would record their hippocampal activity during learning, identify the correct neural patterns associated with successful memory encoding, and later, during other trials, stimulate their hippocampus with those patterns to see if it helped them remember. The results were encouraging almost beyond expectation. In a study published in 2018, stimulating with the prosthetic patterns led to about a 35% improvement in memory performance on average. In some tests of short-term recall, it was as high as 37% better than the person's baseline without stimulation. This was the first demonstration that a memory prosthesis could enhance memory in humans, essentially writing in neural codes that made the brain's own memory formation more effective. It's worth pausing on that result, a one-third boost in memory ability, achieved by an implant playing back a neural code. This wasn't a case of general brain arousal or a motivational placebo. It was specific to when the device delivered a pattern stimulation that mimicked the person's own hippocampal code for a correct memory. When the device was off or when random patterns were delivered, no such improvement was seen. In other words, the device was modeling part of that person's memory processing and then driving the brain with it. It's as if the prosthesis learned the brain's language for, this is what a successful encoding looks like, and then spoke it back at the right time. Even more striking, these human trials, led by teams at Wake Forest and USC, funded by DARPA's Restoring Active Memory program, showed that both short-term memory, a minute or so, and even longer-term memory, recalling items after hours, could be improved by the stimulation. The implication is profound. Memory, at least in these tasks, can be assisted by artificial means in a lasting way. It opens the door to a future where if someone has a brain injury or early Alzheimer's, an implant could help encode new memories that otherwise would be lost. But before we proclaim victory, we must consider what kind of memory we are dealing with, and what exactly is being restored. In these initial prosthetic studies, the focus has been on episodic memory, the ability to remember events or items in context, like recalling a list of words or the image you saw a few minutes ago. This is the function known to critically depend on the hippocampus. Patients like HM illustrate that loss vividly. The prosthetics are not aiming, at least not yet, to restore older memories or procedural skills. They target the encoding phase of memory, effectively boosting the writing of new information. So one might ask, we truly writing memories, or just improving the likelihood the brain stores something? The answer seems to be the latter. These devices don't implant a rich, conscious memory of something the person never experienced. We're not downloading new knowledge matrix style. Rather, they facilitate the person's own memory formation process, a subtle but crucial difference. In essence, the prosthesis provides a scaffold or guide for the brain to strengthen certain neural connections, thereby improving memory retention. It's more teacher than hard drive. It nudges the brain toward the correct pattern, and the brain then does the remembering. Indeed, evidence suggests that the stimulation-induced improvements rely on normal memory mechanisms like synaptic plasticity. When the prosthesis drives CA1 in rats or humans, the downstream circuits, in cortex, appear to undergo LTP-like changes, effectively consolidating those memories better because they received a clearer or stronger signal at encoding. The prosthesis isn't simply an artificial storage that later replays an experience on demand. that science fiction scenario remains far off. It is a catalyst that helps the brain store the memory more effectively itself. This is an important clarification of the role of these devices. They work with the brain's own processes, rather than bypassing them completely. Even so, the notion that an algorithm can substitute for part of you is philosophically jarring. It forces us to consider memory as an engineering problem, one of signal processing and coding. From that perspective, the hippocampus is a transcoder. It takes inputs and converts them to a different code optimized for storage and retrieval. And if we can decode that transcode operation, we can clone it in hardware or software. The work by Berger and colleagues provided a proof of concept that such decoding is possible to a degree. But the hippocampus, as we've learned, is no simple circuit. It's highly recurrent, state-dependent, and context-sensitive. Unlike a straightforward sensory system where we can map, say, pixel inputs to recognized objects, the hippocampal code is more like storytelling than image processing. It's contextually sensitive and nonlinear. As one researcher quipped, the hippocampus is a chaos engine. It will not output the same activity for the same input if the brain state is different or if prior memories interfere. Nonetheless, it appears to have statistical regularities that a model can capture. The MIMO models, for instance, don't decode a specific memory. Red triangle means your keys are on the table. We're nowhere near that. Rather, they approximate the transform the hippocampus applies. Think of it this way: if you can't predict exactly what story the hippocampus will tell, you might still identify its grammar. Berger's approach was to nail down that grammar in the form of a polynomial model that could predict what CA1 would do given what CA3 did, on average and over many instances. The success of memory prosthetics so far suggests that, remarkably, a part of our memory process is reproducible. At some functional level, it's not magic, it's signals in, signals out. Current and cutting-edge efforts. The DARPA program that funded much of this was aptly named Restoring Active Memory, RAM, launched in 2013 with the ambitious goal of developing fully implantable, closed-loop memory prosthetics for brain-injured warriors. Within just 5 years, it yielded the human results we discussed. But that was RAM Phase 1. DARPA also initiated a follow-on effort called REM Replay, or REMRE, aimed not just at immediate encoding but at leveraging the brain's offline memory processing, the replay of experiences during rest and sleep, to improve memory consolidation and skill learning. The idea here is to tap into how the hippocampus replays neural activity. For example, during deep sleep, the hippocampus spontaneously emits ripple events that recapitulate sequences of the day's events, which is thought to help strengthen those memories in cortex. RAM Replay seeks to modulate this process, perhaps by well-timed cues or stimulations, to enhance how effectively memories are solidified. For instance, if a soldier practices a new skill, like a series of room-clearing tactics, during the day, could a device monitor their hippocampal ripples that night and gently stimulate or cue the same patterns, thereby boosting the natural replay and resulting in better retention of the skill the next day? Early research outside of implants has shown that simply presenting a cue, like an odor or sound associated with learning, during deep sleep can improve later memory for that learned material, presumably by biasing the brain to replay that memory. The REMRE program is exploring invasive and non-invasive methods to do this more directly. We are, in short, not just trying to restore memory in the injured, but enhance memory in the healthy, moving from therapy toward augmentation. With these advancements come new neuroengine strategies. A recurrent theme is the importance of closed-loop systems. A memory prosthesis must be smart. It should sense the brain's state and deliver interventions at the right time, in the right way. One straightforward example is phase-locked stimulation. As we noted, during theta oscillations the brain phases between encoding and retrieval modes. If an implant wants to help encoding, it might watch the hippocampal EEG and only stimulate at the theta phase that corresponds to maximal encoding receptivity. Delivering a burst of stimulation at the wrong phase might do nothing or even impair performance, whereas at the right phase it could significantly improve memory encoding. Indeed, in rodent studies, coupling stimulation to the peaks or troughs of ongoing theta has been shown to influence whether the animal is more likely to store or recall information. Another example of closed-loop control is the approach of a University of Pennsylvania team, also under DARPA's program, that took a different tack from Berger's. Instead of modeling the hippocampal code in detail, they developed a system to monitor the brain's electrical activity patterns and predict when the brain was in a poor encoding state. They used machine learning on intracranial EEG signals to detect moments when a person was likely to forget, perhaps due to distraction or fatigue, and only then delivered a tiny stimulation to jolt the circuits into a better state. This approach yielded about a 15% improvement in word list recall tasks. The stimulation was delivered to lateral temporal cortex or hippocampal areas, and only when needed. This is a different philosophy. Rather than insert a specific memory code, it's more about providing a timely push, like tapping a dozing student to pay attention at just the right moment. It's a reminder that neuroprosthetics can work at multiple levels: signal simulation, Berger's method, or state modulation, Eupen's method, or both. Modern neuroimaging is thus embracing adaptive, closed-loop designs. The prosthesis doesn't just run blindly, it listens and adjusts. For example, the next generation of devices might incorporate engram theory insights, the idea that only a subset of neurons, an ensemble, actually encode a given memory. Suppose scientists manage to identify which specific cells in CA3 are encoding a new memory. Some research in mice uses immediate early genes to tag engram cells. A future prosthesis might target stimulation to just those cells or patterns, rather than broadcasting uniformly. While we aren't at the point of reading individual memories, animal studies by Susu Mutongawa's lab have demonstrated that activating a tagged ensemble of hippocampal neurons can trigger recall of a memory even out of context, and even create false memories by pairing activation of a memory ensemble with a new unpleasant stimulus. This shows that at least in rodents, a particular pattern of cells in hippocampus is the engram for a specific memory. Turn it on, and the mouse remembers, expresses fear of something it never actually encountered. Translating this to humans is far often fraught with ethical issues, but conceptually it suggests that a prosthetic could be very precise if we knew how to pinpoint ensembles. In the nearer term, prosthetic systems might implement a kind of memory tagging function analogous to an engram. For instance, if the device's algorithms detect that a current experience is extremely important, say, a life-and-death situation, or something emotionally charged, it could mark that memory for extra consolidation by delivering stronger or repeated stimulation. Think of it as the device internally flagging, "Remember this." In a natural brain, the likelihood of storing a memory strongly does depend on such factors: emotional arousal via the amygdala, novelty signals via dopamine, etc. A prosthetic could monitor physiological signals of these factors, heart rate, pupil dilation, amygdala activity, and decide, this event is salient, I will allocate more resources to ensure it's stored. Conversely, it might go easy on mundane or trivial memories to avoid clutter. These notions blur into enhancement territory, using a prosthesis not just to replace lost function, but to shape and optimize memory according to certain priorities. The interplay between the hippocampus and the rest of the brain is also driving new designs. As mentioned, the hippocampus doesn't work alone. It's part of a broader network including the prefrontal cortex, PFC, which is involved in strategies for encoding and retrieving memories, like mnemonics or contextual cues, and other structures like the amygdala, for emotional tagging of memories, the basal forebrain and locus coeruleus, which modulate arousal and attention affecting memory, and the default mode network, which may underlie internal memory retrieval and mind wandering. An advanced memory prosthetic might become a distributed system. Hippocampal electrodes could be paired with, say, a cortical EEG cap or a wearable that monitors physiological stress, and maybe even stimulators in PFC or amygdala. In principle, such a system could monitor the entire memory ecosystem. For example, if the prosthesis detects the user is trying to recall something but is in a high-stress state, which normally impairs recall, it might adjust its stimulation to calm the circuit or engage a different strategy, perhaps biasing more towards context reinstatement. We can envision a closed-loop network where the hippocampal interface works in concert with cortical sensors and stimulators. One concrete idea already tested in research, pairing hippocampal stimulation with knowledge of sleep stages. During slow-wave sleep, the brain does a lot of memory replay and consolidation. A prosthetic could detect when the user enters the critical non-REM sleep stage with sleep spindles, and then replay its recorded hippocampal patterns from learning sessions earlier that day. Instead of relying on a perfume or sound to cue memories during sleep, as in some experiments, it could directly inject the neural representation of those memories at opportune times, potentially strengthening their consolidation. Early trials of sensory cueing have shown improved recall the next day, so this direct approach could be even more potent. The prosthesis thus wouldn't just help form memories in the moment, it could help refine them overnight. Of course, all these enhancements come with major caveats and concerns. The more powerful a memory prosthetic becomes, the more we have to worry about unintended consequences. Memory is not a simple accumulation of data, it's an active, dynamic process. We forget for a reason. We abstract and generalize and even distort memories to help us make sense of the world without being overwhelmed by details. So, a prosthesis that unthinkingly makes everything stick might actually be detrimental. Imagine never forgetting a trivial detail, or being unable to let traumatic memories fade. The goal must be not maximum memory, but optimal memory for the task of living. The researchers in this field are well aware of this. That's why emphasis is placed on things like selectivity and context awareness. The ideal device should strengthen the right memories at the right time, and perhaps even help suppress or allow the natural fading of others. It might, for example, detect signs of emotional distress when a memory is being recalled and decide to disengage or dampen activity to avoid reinforcing a traumatic loop. In essence, it may need a built-in ethical or safety framework, a kind of moral GPS, that prevents it from causing harm. Already, neuroengineers talk about setting guardrails, limits on stimulation intensity, watchdogs that shut the system off if unusual patterns occur, and user-controlled overrides. Perhaps the user can willfully activate or deactivate the memory assist, maintaining agency. The challenges in translating all this to a real-world medical device are immense. On the technical side, there's the issue of the interface hardware. Electrodes in the hippocampus must be incredibly precise because the hippocampus is deep and small. Most human trials so far have used depth electrodes, similar to those used for deep brain stimulation or epilepsy monitoring, essentially fine wires with contacts along them that are inserted into the hippocampus. These can record local field potentials and some multineuron activity. But long-term, one would want more refined, stable recordings perhaps from many single neurons, which might require advanced electrode arrays or even novel technologies like microLED optogenetics or nanowire probes. The implants have to last years, not just months, without causing damage or scarring that would degrade signal. Biocompatible coatings, flexible materials to move with the brain, etc., are active areas of R&D. Then there's power and telemetry. A fully implantable device needs a battery or wireless power link and a way to transmit data out, or in, without a cable crossing the skull. Modern devices use induction charging and low-power radios like Bluetooth. All that has to be done with absolutely minimal heat dissipation. The brain cannot tolerate more than a couple of degrees of heating. The processing of the neural signals ideally would happen on device, on an implanted chip, to avoid streaming raw data out at high bandwidth, which would eat power. We're talking about effectively a neural coprocessor embedded in your head that runs a memory encoding algorithm in real time, on maybe a few milliwatts of power, with no chance to reboot if something goes wrong. This is an engineering challenge on the order of what it took to make the first pacemakers and cochlear implants, perhaps even more complex given the adaptive nature of the system. Then we confront the variability and plasticity of brains. No two hippocampi are exactly alike in their wiring. The prosthetic model will certainly need to be personalized for each user. A model trained on one person's CA3-CA1 mapping likely won't work on another's without retraining. Fortunately, the device can train itself on each individual by observing their neural activity during memory tasks. But what about over time? The brain isn't static. New memories form, connections change. Will the same model work a year later, or will it slowly become outdated as the person's brain reorganizes, especially if the prosthesis successfully allows them to learn new things, which will alter synapses? This calls for the prosthesis to be adaptive, perhaps employing machine learning techniques that continue to update the model weights as more data comes in. Indeed, researchers have begun to implement adaptive algorithms where the device does a kind of reinforcement learning. It tries a stimulation pattern, checks if the memory was successfully recalled, maybe by monitoring the user's behavior or even a reward signal, and then adjusts its parameters accordingly. In a sense, the prosthesis and the user co-evolve. The user's brain adapts to the presence of the device, and the device adapts to the brain's gradual changes. This dynamic dance is complex, but essential for a long-term implant. We've seen analogous adaptation in motor neuroprosthetics, where users and decoding algorithms jointly learn to improve performance. All the while, safety and ethics loom large. Memory is deeply tied to identity. A device that modifies memory raises questions of autonomy, authenticity, and privacy that go beyond those for, say, a device that helps you move a cursor on a screen. For instance, how do you ensure the user knows which memories were assisted by the device? Some ethicists suggest that prosthetic enhanced memories should perhaps be marked in some way in our introspection, akin to how an edited photo has metadata. One might imagine the device could signal subtly when a recalled memory was one it had a heavy hand in, maybe a distinct feeling or a note in a companion app. This transparency could help the user trust their own recollections, to avoid the eerie feeling of, is this my memory or the device's? Moreover, data security is paramount. The device will inevitably log data, what it stimulated and when, maybe even some neural signals, for its own operation. Those logs are essentially a diary of the user's life experiences in neural code. Such data must be encrypted and protected with extreme care. We have to prevent scenarios of hacking or misuse. One shudders at the thought of memory-modifying implants being compromised by malicious actors or used to manipulate someone's recollections. Ethically, we also face the potential for memory augmentation in healthy people. The original goal is therapy, restoring memory to those who have lost it due to injury or dementia. But if the technology matures, it could be tempting to use it for cognitive enhancement in normal individuals, students trying to ace exams, professionals wanting an edge in absorbing information, or soldiers aiming for perfect recall of mission details. In fact, DARPA's involvement is partially motivated by military needs. Imagine commandos who can flawlessly remember complex briefing details or language translations after brief exposure. If some people had access to memory boosts, what does that mean for society? We already worry about inequality in access to education or drugs. What about inequality in fundamental cognitive ability? Could memory capacity become a commodity, creating a new class divide? There's also a psychological side. Memory is a double-edged sword. The gift of forgetfulness is part of our mental well-being. Our minds perform a marvelously adaptive editing of our past, smoothing over failures, dimming painful moments, keeping what's salient and discarding the rest. A world, or person, with total recall might sound attractive when cramming for a test, but in practice it can be nightmarish. There are people with hypothymesia, extraordinary autobiographical memory, who recall nearly every day of their life, Many say it's burdensome, cluttering their mind with detail and making it hard to move on from tragedies. As one author put it, memory is not just about retaining information, it's about curation. A memory prosthesis should ideally assist that curation, not just turn on a fire hose of raw recording. Designers of these systems are aware, the goal is appropriate fidelity, not maximum fidelity. Perhaps the device could even learn to help forget safely, identifying when a memory trace is causing pathological grief or flashbacks and gently suppressing its reconsolidation. We already see glimmers of this in research on PTSD. Some studies aim to disrupt traumatic memories by stimulating during recall in a way that alters the reconsolidation process, effectively rewriting the memory with less emotional charge. A memory prosthetic could, in theory, perform a therapeutic intervention by detecting when a traumatic memory is being re-experienced and then guiding the hippocampus to recode it in a safer way, for example, pairing it with an input that signals safety, or engaging frontal regulatory circuits. This strays into treatment of psychiatric conditions and again raises ethical flags. Who decides what memories should be dampened? But it might offer relief for those haunted by intrusive memories. Ultimately, implementing a wise memory prosthesis will require an integration of neuroscience, engineering, and human values. Technically, it must have multiple modes: writing, when appropriate, staying silent or even erasing, when appropriate. It must be deferential to the user, perhaps even taking commands like, "Help me remember this," or, "I'd rather not dwell on that," via either conscious input or biometrics. Imagine a subtle gesture or even a neural signal, maybe a specific thought pattern trained as a trigger, that tells the device to bookmark a moment, or conversely, to let a memory fade. The device becomes a partner in one's cognitive process, not unlike an ever-present personal assistant. This demands that it be transparent in operation. A user should never be in doubt about whether a memory was natural or device-influenced. Achieving that might involve some alert or an accessible log the user can review. Perhaps your smartphone, linked to the implant, might show a timeline. These events today were given enhanced encoding by your hippocampal prosthesis. This could help maintain a sense of ownership and reality. The road from the prototypes in the lab to an everyday clinical device will likely span many years and careful trials. The encouraging human trial results so far were in controlled environments and small N. The next steps include testing in populations that truly need it, patients with early Alzheimer's disease or memory impairment from brain injury. Will the prosthesis provide a noticeable improvement in their daily life function? It's one thing to boost scores on a memory game, it's another to help someone remember faces, appointments, or where they left the stove on. Those are much more complex, real-world memories than the simplified tasks used in research. There is hope, though. The hippocampal codes for spatial navigation and events are exactly what goes wrong in Alzheimer's. One of the first signs is getting lost or repeating questions. A prosthesis that reinforces those codes might extend a patient's independent functioning. But it will have to contend with a disease process that is ongoing and progressive, not a fixed lesion. This again points to the need for adaptability and maybe modularity. Perhaps future neuroprosthetic systems will be hybrid, combining hippocampal implants with drug therapies or genetic therapies that slow the underlying neurodegeneration. As we push forward, one almost poetic twist emerges. In building devices to restore memory, we end up illuminating memory itself in new ways. The engineering forces clarity. You have to define what exactly you're trying to restore. Is it the ability to form any new memory, or specific types? Does it include context and emotion or just factual content? In grappling with these, researchers refine the theories of memory. For example, these prosthetics implicitly target declarative, contextual memory. They don't target skills or habits, those reside in different circuits, striatum, cerebellum. So if someone with a prosthesis learns to ride a bike, it won't be via hippocampal implant but via normal motor learning. The device might help them remember that they practiced bike riding, but not actually improve the procedural learning of it, unless one day we have prosthetics for the striatum too. Similarly, we might eventually have to classify different aspects of an episodic memory, the who, what, perhaps processed in lateral temporal cortex, the where, hippocampal place cells, the emotional tone, amygdala, and realize a single hippocampal prosthesis is just handling one piece of that puzzle. That recognition could lead to multi-region prosthetics or to acknowledging limits of what can be done in one region alone. Even more fundamentally, these efforts challenge us to ask what it means to remember. Each time we recall something, we are reconstructing it, not simply playing back a tape. The hippocampus famously injects some randomness and combines memory fragments. It's why memories are fallible and also why they're flexible and useful. If a prosthesis brute forced a memory by imprinting it exactly as encoded, could that rigidify the memory, making it less modifiable or integrable with new information? Perhaps we will need to design stimulation that deliberately leaves room for the natural variability, reinforcing the gist of an experience without locking it in stone. One can imagine the prosthesis delivering a probabilistic cue to recall rather than a deterministic one, nudging the network toward a pattern without fully enforcing it, thereby allowing the brain's own pattern completion to do the rest. In fact, the current devices already work like that. They don't specify every spike, they just bias the population activity in CA1. This may be a blessing, preserving the fluidity of memory. The goal is to help the brain recall enough to be useful, but not to overspecify a memory to the point it can't evolve. After all, our memories change subtly each time we recall them, a process called reconsolidation that updates them with new context. A prosthetic that overshoots and stabilizes a memory too strongly could impair that natural updating. Hippocampal prefrontal interactions deserve a special mention here. In recent research, there is evidence that successful memory retrieval, say, figuring out that yes, you've seen this person before and remembering where, involves a synchrony between the hippocampus and prefrontal cortex in the theta and alpha frequency ranges. The prefrontal cortex might send a cue or query, the hippocampus produces a candidate memory, and then the prefrontal either accepts it or asks for more evidence. If we place a prosthesis in the middle of this loop, we have to ensure it doesn't muck up this delicate exchange. One intriguing future path is to include the PFC in the loop, maybe record PFC activity to gauge when the user is attempting a recall versus just passively experiencing, and use that to time stimulations. Or use PFC signals of confidence or error monitoring to decide when to trigger a memory replay. Already, BCIs for other cognitive domains, like attention or mood, are exploring multi-region interfaces. Memory prosthetics might become part of a larger cognitive neuroprosthetics framework, where various nodes of the neural network are all given a bit of support in concert. As the lecture draws to a close, we find ourselves at a precipice between the known and the speculative. On one side, there is what we have achieved. We have identified some of the neural codes of memory, reproduced them in silicon, and by doing so, partially restored a cognitive function once thought too complex to ever repair. A person, wired up in a lab, has remembered better because of a device inside their head that alone is historic. On the other side of the precipice lies a landscape of possibilities, implants that boost learning capacity, that merge human memory with external storage, or connect multiple brains. One could imagine someday using similar technology for brain-to-brain memory transfer in some form, though that remains very much science fiction. We must step carefully into that landscape. Each advance will raise new questions of safety, selfhood, and social consequence. Yet, if done responsibly, the potential benefits are profound. Millions suffer from memory loss, from Alzheimer's, traumatic brain injuries, chronic epilepsy, and more. For them, a neuroprosthesis isn't about becoming superhuman, it's about regaining the most human thing of all, the continuity of experience, the ability to keep living life forward rather than stuck in an eternal present or fragmentary past. In developing these devices, we also force ourselves to articulate a philosophy of memory. We have to program into them answers to questions like, what should be remembered? What can be forgotten? How do emotion and meaning factor in? These are questions humans have pondered for ages in literature and art. Now they become engineering parameters. It's a bit humbling and exhilarating to realize that by engineering memory, we are in a way holding a mirror up to our own souls. We are learning what it truly means to remember, by trying to build a machine that remembers. In closing, consider that man in the kitchen with the coffee cup. In the current day, if his condition is like HM's, no pill or therapy can restore his ability to form new memories. His world remains a series of disjointed moments. But perhaps in the not-so-distant future, he could have a device implanted that provides the missing link, a bridge, so that what happens now can reach tomorrow in his mind. He might once again greet his wife with recognition each morning, learn the layout of a new home, even form new treasured memories of grandchildren. The device would not be giving him anything alien, it would simply be restoring what was once his, the natural capability to tie his life together with the thread of memory. And if we can achieve that, it will rank among humankind's greatest technological and biomedical triumphs. We will have cracked open the door to the inner library of the brain and found a way to patch its pages. But with that triumph comes the responsibility to tread with care. For memory is the essence of experience, and in shaping it we are, in a very real sense, shaping the story of a person's life. Memory prosthetics and hippocampal interfaces thus represent both a magnificent technical achievement and a profound human endeavor. They force us to combine hard science with deep humanity. As engineers and neuroscientists press on with chip designs and computational models, they do so always with an eye on the individual who might one day rely on this device, an individual who wants nothing more extravagant than to recognize a loved one's face, to remember yesterday and imagine tomorrow. The hippocampus has been called the doorway to memory. Through that doorway, we step into our own lives, continually. With these new neuroprosthetic technologies, we are building a new doorway, one that, we hope, will remain open when the biological one has closed. It is a bridge across time, made of electrodes and algorithms, yes, but ultimately in service of something fundamentally human, the continuity of self that memory allows. And in that sense, even as this technology is cutting-edge and computational, it is also deeply poetic. It speaks to the resilience of the human spirit, that we would dare to engineer our way back to wholeness, to refuse to surrender our stories. We stand at the threshold of that new frontier. The science is young, the challenge is many, but the direction is set. In deciphering the neural code of memory and learning to replay it, we have begun to learn the melody of memory. Now we must learn to play it wisely, in harmony with the brain's natural symphony. The promise is that one day, losing the hippocampus will no longer mean losing oneself. Memory, aided by a prosthesis, will continue to be memory, fallible, personal, richly woven, and ours. The device will simply ensure the threads don't snap, that the tapestry of our life can continue to be woven even in the face of injury or time. In doing so, these hippocampal interfaces do not diminish the wonder of memory, if anything, they underscore it. For they show that even when memory is treated as a signal to be engineered, its end purpose remains profoundly experimental and human, to remember, to learn, to connect, and to carry forward the story of who we are.